12.2, we're going to take a look at differentiation and integration. And as with most other things that we did in 12.1, it's going to look a lot like things you've done in Calc 1, right? We're going to do differentiation and integration. Now the notation, of course, is a little bit different because we are working with vector valued functions. So the derivative of a vector valued function r of t is r prime of t. It's the limit of delta t as delta t goes to 0 of r of t plus delta t minus r of t over delta t. This is true for all t for which the limit exists. If r prime of t exists, then we call r differentiable. And if r prime of t exists for all t in an interval, we would say it's differentiable on I. So a little bit of notational differences, but everything really mimics Calc 1 with what you learned about derivatives in Chapter 2. Okay. So Theorem 12.1 talks very specifically about how we go about doing this for a vector valued function. So if our vector valued function r of t is f of t I, g of t j, and h of t k, right, addition, then we just take the derivative of each component, just like we would have expected.
Will we do vector value functions that are not like independent of each other?
You mean like to separate pieces like this?
Yeah.
Okay. No, they all have this feature. Okay, so we're going to find the derivative. So we're going to pause for a moment, and I'm going to pause anyway, and you're going to find the derivative of all three pieces. All the derivative rules that you saw and have seen throughout are valid to use, okay? So, chain rules and product rules and all the things, right? You might see some transcendental functions or trig functions involved, different things like that. So go ahead and find the derivative of r of t here. And then we'll check together. And you can write it component-wise the way they've written it, or you can write it with the ijk's in an equation, more of an equation kind of perspective. It doesn't make any difference. Okay, so what rule is present on the first problem? It's a chain rule. What did you get, Alex, for your derivative?
2t e to the 2t squared. I mean, e to the t squared.
Okay, does everybody else get that piece? Looks like that? Very good. What rule do you see on the second one? Product. And actually a chain as well, right? There is a chain inside of it. It's not a very exciting chain, but there is. Okay, so somebody give me what you have for this one for the derivative.
2t e to the 2t plus 2t squared e to the 2t.
Okay, so yours look like that? Or maybe flipped. Yeah? Good. And what property or what derivative rule are we seeing on the last one? It's trig and chain rule. Very good. Maggie, you want to tell us what you have?
2 secant 2t tangent 2t.
Very good. Does everybody else have that one? Okay. If there were any cleanup we could do, we would do so. There isn't here. There's nothing to simplify and so forth, so we're finished. Now, on our next problem, we're actually going to put a lot of the things that we've been doing with vectors in Chapter 11 and vector valued functions from 12.1 together. So the first thing it asks us to do is it gives us a list of things. It's going to ask us to find the derivative, the second derivative, the dot product of the first and second derivative, the cross product of the first and second derivative, and then it gives us the actual function, vector function itself. So the first thing we're going to find is r prime of t. So this one is a little bit friendlier than the last one. There's less going on. Whoops, let's try and move that over here just a little bit. All right, so what's the first derivative? The derivative of the first piece, sorry. T. So ti. And again, if you don't like the ijk notation, you can change it out or you can leave it this way. How about the derivative of the j component?
1.
-1, or you can write just negative j. How about the derivative of the k component? 1/2 t squared k. Excellent. And then we're going to do the second derivative, and it's just exactly what you would expect, right? The derivative of the derivative. So what do we get for the second derivative here? I. And then?
Plus
Yeah, 0 in the middle, so then we move on to the plus part at the end. Plus, what'd you have, Alex?
TK.
TK. Do we have those? If you want to write the 0 in, because we're about to do some dot products and some cross products, that would be perfectly reasonable to have it written there as a reminder to yourself. If you don't want to or you need to see it written, that's fine too. So the first one is a dot product. We haven't done a dot product in a bit, so, well, at least not together in class. So how do we do a dot product, remember? What's that process?
Multiply the x components, the y components, and the z components.
Right.
And add all the...
Perfect. So the components they're the values that are written beside the i's get multiplied. So the first I is t, and the second coefficient of I is 1. Plus, and then the first coefficient, or the coefficient in front of j is -1. And the second coefficient for j is actually 0. That's the one I didn't write in, but maybe you did. And the last one, the k component, is 1/2 t squared. And the second k component is a t. So we need to clean it up a little bit because, there's no reason to leave it written messy. So the first one is t. The second one is 0. I'm just going to not write it. The last one's what?
1/2 t cubed.
Yep. So plus 1/2 t cubed. Remember, dot products give us a scalar multiple. This is a scalar multiple if we have a value for t. This would be a scalar. So there's no ijk component. And the last part of the directions is to take the cross product of r prime and r double prime. So I'm going to write out the determinant form. So if you remember, this is ijk. And we'll put all of the coefficients for r prime in first. So that would be t, -1, and 1/2, I need some more space, 1/2 t squared. And then for the second one, I would have 1 and 0 and t. So we expanded along minors. Remember that terminology. And so if you'd like to see that step, I'll show it on this one. If you can jump forward through that step and don't want to show it, and you're just showing some of the multiplication pieces, that's okay too. So I'll show you what I mean by that in just a second. But one option is to write out each of the three 2 by 2 determinants. So -1, 0, 1/2 t squared, and t, like so. Then we have minus j. We'll do the same thing with j components. So we'd have t and 1 and 1/2 t squared and t. Okay, I think I got those written in right. I didn't write this part on my notes, so that's why I'm double checking. Okay, and then the last one, is the k components, or the k unit vector, or determinant. T1, -1, 0. Okay, so if you need to see that, feel free to show that. I've shown that on most of the ones that I've done in class. Or you're welcome to jump to the next step where you actually see the multiplications. This is I times, and it's -1 times t, and then minus the 0. So remember, we multiply down, subtract multiplying up. So that's the first one. I have minus j. I multiply down, I get t squared. I multiply up, I get negative. And subtract, I get -1/2 t squared. And then for my k component, if I multiply down, I get 0. If I multiply up, I get -1, but then, so 0. But it's in subtraction, so it's actually +1. So as long as you show me one of these steps, right, that would be enough. The second step is actually the one that I have written in my notes. So this is, let me get my hat on I, everything else had it, okay. So negative ti, looks like I've got negative 1/2 t squared j, and then, okay. Okay, does that look good? Everybody good with that? All right. So we're going to cross paths with a word that you've seen before. The word is smooth. So we will say that a curve traced out by a vector function, in the same form we've seen it in, is smooth on an interval if the derivative is continuous and the derivative is not equal to 0 except possibly at the endpoints. So if it fails to be continuous or fails because it has r prime is not equal to 0, it's equal to 0, right? Then that means it's not going to be smooth at those locations. So those are our two conditions that we test. We test for continuity and we test for derivatives being equal to 0 or not equal to 0, likewise. Okay. Okay, so we have one that's given to us. Are you good?
Yeah.
Okay, everybody got it. Wonderful. So we're given this one's actually just got it's 2, right? 2 component vectors instead of 3 components, and it's asking us to see if this is going to be smooth. So the first thing we need to know is if the derivative is continuous, not the original function, but the derivative. So in order to do that, we've got to take a derivative to figure out what we're working with. So we'll start by taking a derivative. All right, so this is in component form, so I'll keep it in component form. So if we have t to the 4th minus 2t squared, what's our derivative? Excellent. And then the second component, derivative.
2t minus 3.
Okay, so is that derivative we just found, is it continuous?
Yes.
Yeah, this is continuous. And it's continuous from something we saw in Calc 1, is it's because these are polynomial pieces. So we'll call them f and g because that's what we've been doing before. F and g are polynomials. This is the y.
When it says r prime of t does not equal 0, is
Yep.
that implying that all of the components in?
Yes. So, yeah, over here, r prime of t equaling 0 means whatever, whether you're in a 2 space or a 3 space, you've got to not have this vector. Each piece is 0. Or you could do it for 3 pieces if you had 3 pieces, right? That's what we're looking for. And so that's what we're going to look at next, is we're going to look at the locations, if there are any, where this actually would achieve the problem of having a 0 vector. And in particular, that means we set each component equal to 0 to see what we find. So this is 4t cubed minus 4t equals 0. And we have 2t minus 2 equals 0. All right, so on the first one, we would need to factor. What would we factor out? 4t, which means we're left with
T squared minus 1.
t squared minus 1. So probably you've done enough algebra at this point to look at it from this point and to be able to tell me what the values are when t is equal to 0. So,
0.
or when the function is equal to 0. 0 and
1 and negative 1.
right. So there are 3 options where the first component is equal to 0. How about the second component?
1.
It's just at 1. Now, if these didn't match at all, right? If there was no overlap between what we found for the first component and the second component, it would simply be continuous on the whole domain. Does that make sense? It would be smooth, excuse me, on the whole domain. But these actually have one in common. T is equal to 1. So this one will be continuous, not continuous, smooth. Okay, let me see where I am. This will be smooth on I for all t in I where t does not equal to 1. So it is smooth almost everywhere, right? The one place where it's not smooth is when t is equal to 1 because that's the location where the derivative is equal to 0.
Is I interval
Yeah, so it's defined over here. I is just an interval. Yep. Interval I. Here it is. Yep. That's the notation that they're using, so I just carried it forward in our problem.
Can you go back to?
Yep.
So it says on interval for all t. What does the e mean?
It means is an element of or is contained in. So it's one of the items in it. So it's all the t values in the interval. We're just not going to be able to use t equals 1. Yep. And you can feel free to write it out longhand. I just shortened it
We
for
just have
notation.
written it out in like interval notation.
You could, so you're thinking like to go negative infinity to 1 and then 1 to infinity. You could. They don't specify the interval here, but if they were to specify the interval, then you'd have to pay attention to that.
Okay.
Right? So like if it said that the interval was, 0 to 10 or something like that, you'd have to be more careful with it. But yes, you could do it that way too.
Okay.
Yeah.
So you would just put smooth and then do interval notation?
Yeah, you could say, so this is basically what Alex is asking, is that we say something like this. It's smooth on negative infinity to 1, union 1 to infinity. Okay, I'm off the screen. Sorry, I didn't realize. This is the problem with the black backdrop is as soon as I'm off the screen, I can't tell because the backdrop is running into the black that's on the side anyway. So yeah, all right. So yeah, you could write it like that as well. That's assuming that the interval, right, the I that we're looking at is the entire real numbers, and we don't necessarily know that, but we're not told that it's not either, so it's okay. What if the interval that we were looking at didn't include 1? Right, like what if it said it wants to know about the interval from 10 to infinity? Well, then it would be different. It would be smooth everywhere, right? In that interval too. So that's another possibility. Okay, so this is differentiation. Works mostly like what you've seen. The definition for smooth is a little bit different. We haven't seen a comparable to that, but it's components of things we've done before. So the next piece is integration. So for the vector valued function, again, given as normal, we define the indefinite integral of r on AB as follows. And these are all equivalent components to one another. So there's just different versions of this. But all of them are saying things you already know, right? We're just going to find the integral component-wise, just like we found the derivative component-wise. Take the derivative of each individual piece, we'll take the integral of each individual piece. Okay. Oh, a couple you're still right, sorry. Okay, is everyone good? Good back? Okay. All right, so we're given one that's in the IJK form. We have the integral, and we've got 2t minus 1i, 4t cubed j, and then 3 square root of tk. And we're going to do this component-wise. So what is the integral of 2t minus 1? We'll call this r of t. It's capitalized from, from notation we've seen before. I can't remember if I actually defined it. I didn't, but it's the capitalization notation that we see in Calc 1.
Do you have plus c?
So we do. And the problem is we're going to need a plus c in each location, and they don't necessarily all have to be the same c. So what we're going to do is we're going to do plus C1. The book may call it K1. I'm going to avoid using K because we're using K for another purpose here. But you need a constant at the end of it, and we're going to have 3 constants, so I'm going to go C1. It used IJK notation. I'll do that too. So all of this I. All right, so what about the J component?
2 to the 4th.
Mm-hmm. T to the fourth, but then it needs to be also plus C2, and that's J. And then the K component is the, like, ugliest, for sure. 2T to the 3 halves, but it was given to us in radical form.
So 2 square root of t to the third.
Okay, you can do square root of T to the third. What's another way you could write it?
2T square root of T?
You could. So there's a couple different versions. As long as it's in radical form, either the one that Robert said or the one that Adeline said, is either of those are fine. So
But it does have to
those
be
are fine.
radical form.
It needs to be in radical form because it started out that way.
Okay.
If it had started out in exponential form, like with the exponent being a rational exponent, that would be fine to leave it that way. But we're going to do this one right the other. I've got this one in my notes and I wrote it last, so I'm going to go with this one. And then it's plus C3 and it's K. Okay, and if you're looking at this and you're going, wait a minute, remind me what they did with those radicals again? Let me just show you real quick. Hang on. Hello. This square root of T is 3T to the 1/2. We add 1/2, it becomes 3 halves. 3 halves would be the divisor. So we divide by 3 halves, which means multiplying by 2/3. So 2/3 times 3 gives us 2. And then the new exponent is 3 halves. 3 halves written back in radical form is the square root of T cubed. Okay, everybody good with that? Remember how the radical stuff works? Wonderful. Okay, so the next one actually has A's in it. A is just a constant, doesn't really do anything any differently, but just be aware of that. But it also wants us to do, this should say the definite integral. This is what happens when you copy and paste things. This should say definite integrals, so change that. We're going to evaluate the definite integral. And it's the integral from 0 to pi halves. And we have the a cosine ti, a sine t, j, and k. So we're going to find our antiderivatives, and then we're going to evaluate. And remember, when we do definite integrals, we don't do plus c's because they cancel themselves out when we're doing the addition and subtraction components. So we don't have to worry with that. So what is the antiderivative of a cosine t?
A sine t.
Yes, a sine t. And again, they're using I to k, so I will as well. How about the antiderivative of a sine t?
Minus a cosine t.
Yep, minus a cosine t. And that's j. And then the derivative of, antiderivative, of k.
KT.
Yep. And we'll put the t first, but yeah, t and then k. Is that good for everyone? Okay. So then we're going to evaluate this at pi over 2 and at 0. And while I could evaluate everything at pi over 2 and then evaluate everything at 0, it's easier to do it within each component to do the evaluation so that it looks something like this. Within my first component, if I evaluate at pi over 2, I have a sine pi over 2 minus a sine 0. And that's I. And then I have, I'll do plus and negative, plus, and then I have negative a cosine of pi over 2 and minus, well, it's minus a negative now, so plus a cosine of 0. Did you have a question, Maggie?
Your I component, shouldn't it be negative a? The derivative of cosine is negative sign.
We're not taking derivatives, we took antiderivatives.
Integral.
Yeah, integral.
That would make sense.
Yeah. Is it good now?
Yes.
Okay, no problem.
Sorry.
And then our k component would be pi halves minus 0. I actually talked about that. We're doing integration by substitution in my Calc 1 class, and I talked about the fact that this is the point we need to be really careful because we're going back and forth within the same problem, and trig functions, those negatives can catch us. So, all right, so let's just evaluate some of these individual pieces because these are all unit circle values, right? I mean, not the k part at the end, but the trig pieces are. So what is sine of pi over 2?
1,
Yeah, so this one is 1. How about sine of 0?
0,
That one's 0. Cosine of pi over 2?
0,
That one's 0. And cosine of 0?
1.
1. Okay, so using those features, the first piece will actually give me just a, and that's it. And then times my I. And the second component will be what?
A,
Yeah, it'll be another a, so plus a, and then the component j. And then what will be the coefficient of my k component?
pi over 2.
Yep, pi halves k. And again, if I had value for A, right, like an actual coefficient number that I could see it, this would actually end up being vectors like we encountered in chapter 11, right? They just have coefficients that are all constants, and A is representing a constant here. All right, I think there's one more. Paper open. So these are what we call initial value problems. We did them in Calc 1 as well. This is just Calc 1 2.0, right? That's what we're doing. So we have this one's got just two components. It's an ij. And they're telling us that the vector r of 0 is 2I. So we're going to take a look first at finding, it says find an r of t that satisfies the initial condition. So this initial condition is the last thing that we're doing. We're starting by taking the antiderivative of both sides. Now, the antiderivative of r prime would just be r. There's no capitalization because I'm just removing the prime notation. So this is r of t on the left. What is the antiderivative of 4e to the 2t?
2e.
Mm-hmm. So we would divide by the coefficient of the inside term, or you could think about doing a u substitution, a really simple u substitution for that. And we would have this as being plus c1, okay? So all this plus c1 is the I component. And then what is the antiderivative of 3e to the t?
3 over t to the t?
Nope.
No? Oh.
It's itself, yeah. It's 3e to the t.
Oh, okay.
Yeah, it's one of those ones. And then I need plus c2. And this is j. So this is what we would have done on problem number 4 above. We would have just stopped here and we would be done. We'd have the c1 and the c2 written here, and that's it. The difference right now in what we're doing, though, is that we have the ability to evaluate. And we evaluate based on the initial condition that we were given up here, which is that we have a 0 we're plugging in for t, right? So that's saying 0 is plugged in for t. So we have r prime of 0. And I have 2e to the 0 plus c1 I. Plus 3e to the 0 plus c2 j. And this is supposed to equal the vector 2i, which is 2, 0 in component form. Okay, so I switched, well, I guess I shouldn't do that since I wrote it that way on the left. I've got notation mixed up on my paper to what I'm doing on the board. So we have 2i, and I'm going to put plus 0j. We'll do it that way. So what this is telling us is that the first component, the I components, have to be equal. So in other words, this piece and this piece have to be the same, or we have an equation that says 2e to the 0 plus c1 is equal to 2. And the other one says that the 3e to the 0 plus c2 is have to equal 0. So 3e to the 0 plus c2 must equal 0. So what is 2e to the 0?
2.
It's 2. So the left-hand side is 2 plus c1 is equal to 2, so what's c1?
0.
0. All right, the next one, what is 3e to the 0?
3.
3. So 3 plus c2 is equal to 0. What's c2?
Negative 3.
Negative 3. Everybody good with those two pieces? Okay. That allows us to come back up to where we were right here and to fill in the c1 and the c2. So my r of t, I'll have to write it above because I've run out of space a little bit, but the r of t equation is going to be 2e to the 2t. And there is no c1, so I don't need to write it. And this is I. And then plus 3e to the t minus 3. Well, from the side, yeah, I am. 3 to the t minus 3, j. Make sense? Okay.